3.9 Variation of Parameters. In this section, we continue discussing non-homogeneous ODEs. We introduce a second method for finding y sub p, which you recall is one specific particular solution to the non-homogeneous ODE we were trying to solve. In the last section, we discussed the method called undetermined coefficients, and that section ended with us pointing out that that technique, undetermined coefficients, can only be applied in a limited set of cases. Specifically, we can only apply undetermined coefficients if the g of t is built out of three types of ingredients: exponentials, polynomials, or the primary trig functions, by which I just mean sine and cosine. And actually, those ingredients have to be combined in a specific way. They can only be added or multiplied. In contrast, the method we're discussing in this section is very general. It can, in theory, be applied to any ODE that has any type of g of t. As I note here, the in theory is necessary because this technique will require us to evaluate integrals, and there's always a possibility that we could encounter an integral that we can't directly evaluate. This aspect of this method is actually sort of one of its strengths, as I'll try to demonstrate with our last example at the end of the lecture. What I'd like to do in this lecture is start by laying out a step-by-step description of the method of variation of parameters. Then, before we try the method on examples, I'll provide an explanation of the structure of the method that leads to the steps that we follow. And actually, understanding this general structure will lead us to slightly modify our steps, or just sort of have an alternative method for enacting this technique. So we'll kind of see an explanation of that as well. And then all of this will, of course, be demonstrated through examples at the end. So let's take a look at the steps that are involved in enacting the method of variation of parameters. So our goal here is to find the general solution of a non-homogeneous linear constant coefficient ODE that has this form here. And as always, our first step is going to be to solve the homogeneous version of the differential equation, where we set the right-hand side equal to 0. In the previous section, we explicitly wrote out y sub h at this point. The key ingredients that we need to take away from that homogeneous solution in this method are two functions that serve as a fundamental set of solutions for the homogeneous ODE. So these are just the y1 and y2 that we come up with and would typically build our homogeneous solution out of. And then in step 2, and step 2 is really the key here, we're going to construct a system of equations. Let's look at the ingredients in this system. We've got the y1 and y2 that we just found in the previous step. If I have y1, I can clearly calculate y1 prime, similarly for y2 prime. But the primary ingredients in this system are this u1 prime and u2 prime. u1 and u2 are unknown functions. So we're just going to, in this system, represent them generically as u1 prime and u2 prime. And the purpose of the remaining steps will be to calculate what u1 and u2 need to be. In step 3, we do exactly that. We use this system and we treat u1 prime and u2 prime as the variables, or the unknowns in the system, and we solve the system for u1 prime and u2 prime. When we're done with step 3, we have expressions for u1 prime and u2 prime. So step 4 will involve anti-differentiating those expressions to, of course, yield u1 and u2. Notice here that we do want to introduce constants of integration when we do this anti-differentiation, and we call those constants c1 and c2 respectively. So once I'm done with step 4, I have my u1 and u2. What's the purpose of these two functions? What role do they play in our general solution? Step 5 clarifies this. We build the general solution to our original non-homogeneous ODE by simply multiplying u1 by y1 and then adding u2 times y2. On the top of the next page, the first thing that I note is that throughout this derivation, the left-hand side of our differential equation has always been y double prime plus by prime plus c. Let me show you. Let me scroll back up. And when I state the goal here to solve this non-homogeneous, notice that the coefficient on y double prime is exactly positive 1. In the first step, the coefficient on y double prime is exactly positive 1. So it's just an important note that for simplification in the calculations that we do in this method, we force the coefficient on y double prime to be 1. What if it's not? What if our original differential equation has a 2 in front? Well, we're simply going to just divide the entire equation by that that too, and that'll modify the coefficients in this right-hand side accordingly. So it's pretty easy to force that lead coefficient to be positive 1. So what else can we say about this method? It seems to me that this method is relatively direct. We solve the homogeneous version of the ODE. That simply requires us to find the characteristic polynomial and then build the solution appropriately. We've done that so much, I imagine many of you can do that without writing much down. Then we set up and solve a system of equations. And this system of equations is really the heart of this method. So setting up and solving that system of equations is really the primary work that we do for this method. That yields u1 prime and u2 prime. So then the next step is just to anti-differentiate those. Finally, we combine the u's and y's appropriately, and we have our general solution. So on the one hand, this seems like a pretty straightforward method. On the other hand, this raises some questions, for me at least. First of all, where did that system of equations come from? In step 2 above, we simply stated that there was this system of system of equations that we needed to solve, but where did that come from? Second question is why is our solution u1 times y1 plus u2 times y2? Why does our general solution have that structure? Another question is, where did this equation come from? Why is it true that these two unknown functions, u1 and u2, must satisfy this equation? What I'd like to do next is a general derivation. That is, I'd like to work through the development of this procedure without specifying particular ingredients. So I want to use generic placeholder variables like y1, u1, etc. During this derivation, the notation will get a little tedious, so that's kind of a disadvantage of using this general approach, but an advantage is that this derivation will demonstrate that we really can, at least theoretically, use this method for any g of t, any non-homogeneous function. So let's try this out. I do want to point out real quick, this is not a squared, that's a footnote. So you'll see a footnote at the bottom of the page if you want to read that for a little extra clarification, but we are trying to find the general solution of our standard non-homogeneous linear constant coefficient differential equation. Once again, I've forced this lead coefficient to be positive 1. So if there was a coefficient there, I just divided through it, and then I'm going to label the resulting coefficients b and c on y prime and y, and then the resulting right hand side I'll still call g of t. So as indicated above, I'm going to solve the homogeneous version of this differential equation. So here I've written out that that's going to be our first step to solve the homogeneous equation y double prime plus by plus cy equals 0. I meant to say by prime. And then when doing undetermined coefficients, we really wanted to walk away with y sub h, the general solution to this homogeneous equation. In this case, what we want to do instead is identify these two functions, y1 and y2, that general solution is built out of. So the way that I state that here is I want to label y1, y2 to be a fundamental set of solutions to this ordinary differential equation. And then in this next step that I've already written out here, this is really the crux of this method. I want to suppose that if I was to take unknown functions u1 and u2, multiply them by these components of this fundamental set for the homogeneous solution, for the homogeneous equation, then this resulting function is a solution to our original ODE. That means the original full non-homogeneous ordinary differential equation. And I say that this is for some as of yet unknown functions u1 and u2. So this supposition or this assumption is really central to this method of variation of parameters. Is it fair to assume that there are functions u1 and u2 that will make this function actually a solution to our differential equation? It's hard to justify this answer, but the answer is definitely yes. In fact, there are so many functions u1 and u2 that will yield a function like this that will satisfy our differential equation, that we can actually take the liberty of putting additional restrictions on u1 and u2. So as you'll see in the next couple steps, not only do we need u1 and u2 to be functions such that this will satisfy our ODE, but we can make additional restrictions on u1 and u2. Anyway, since I need this to be a solution to my ODE, I should use the usual trick. Let me identify the appropriate derivatives. Let me plug them into my original differential equation. Here I've reminded myself of the function y. I've calculated its derivative. Since both u1 and y1 are functions, then I need to apply the product rule appropriately. And already this is starting to be a little messy because I've got just the first derivative here and I've got 4 terms that I'm going to have to keep track of. When I take the second derivative, each of those terms will double, so I'll have 8 so this is starting to be a mess. Here's where I'm going to impose an additional restriction on u1 and u2 that will simplify this process and will yield a second equation that we can use in the system that we want to solve in a bit. Specifically, here's what I'm going to do. I'm going to target these 2 terms in my derivative, u1 prime y1 and u2 prime y2, and I'm going to force the sum of those 2 terms to be 0. As I mentioned a second ago, there are so many functions, u1 and u2, that will make this process work that we can actually impose an additional restriction such as this one, and we'll still be able to find functions u1 and u2 that make this process work. So, enacting that assumption, these 2 terms will go away, and my y prime will clean up a little bit. So now let me take the derivative of this new y prime to get y double prime. And now I have the 3 ingredients that I'll need to plug back into my original ODE. I have y, my improved y prime, and then my y double prime. So let me take those ingredients and plug them into my original ODE. Now, there are a lot of terms. There's kind of a lot going on now in this equation here. I've taken each of those derivative and function terms, plugged them in appropriately. Let me zoom in, scroll up a little bit, give myself some space to work with this equation. Oh, just kidding. There is no space for me to work. That's all right. I'll squeeze it in here. I just need 1 or 2 more lines of this computation. So what I want to do in this equation is I want to focus specifically on the u terms that are not derivatives. Notice in this first expression I've got a u1 and then a y1 double prime, and then I've got a u1 prime y1 prime. So this term is like a u derivative term, and most of my other terms are u terms, not u derivative terms. In fact, there are only these 2 u derivative terms. So what I'm going to do is I'm going to sort of isolate those, push those over to the right. So whatever happens in this first part of the equation, I know that I'll have those u derivative terms down here at the end. Next, what I'd like to do is I'd like to group the u terms based on which u they are. So I've got a u1, a u2. So let me go ahead and group all of my u1 terms. And then I'll similarly group all of my u2 terms. And that should account for all the terms in the equation. So if I track down all of these u1 terms, I have a y1 double prime plus b times y1 prime. I'm going to factor out this u. So in the parentheses here, I'll just have a b y1 prime. And then similarly, factoring the u out of this u1, I'll get c y sub 1. Playing the same game with my u sub 2 terms. So, still got a lot going on, but let's see. I've got u1 times all of this stuff. I've got u2 times all of this stuff, and then I've got these extra terms here on the end. So, what were y1 and y2? If you remember, those are fundamental, they form a fundamental set of solutions for the homogeneous version of my differential equation. Well, this is exactly my differential equation. In the parentheses here, I have my original differential equation, the left-hand side, with y1 plugged in. So since y1 is a solution of the homogeneous version, then if I put these terms together in this combination, I know that this entire expression within this set of parentheses will go to 0. The same thing will actually happen for y sub 2 because y sub 2 is also a solution to the homogeneous version of my differential equation. So if I put y sub 2 into this left-hand side, I know that when it simplifies, it gives me 0. So all of these terms are eliminated, they all vanish, and all that remains from this equation is this second part here with these u derivative terms. So, in order to satisfy our differential equation, the only thing that we need to force to be true is this sub-equation here. And now if I recall that these calculations are based on the assumption that this equation must be true, then I now have two equations, both in terms of u1 prime, u2 prime, which must be satisfied in order for this original function to actually be a solution to my differential equation. And if you were to scroll back up, you'll see that these two equations are exactly the two equations that comprise the system that we need to solve to enact this method. So that's the derivation of where that system of equations comes from, and I reiterate that that is built on the assumption that our solution will have this form. So let's go ahead and give it a try and take a look at an example. Example 1, we have a familiar looking non-homogeneous differential equation. And before I get started, I just want to note that this is the type of g of t to which we could not apply undetermined coefficients. How come? You'll notice that this g of t is built out of polynomial and exponential ingredients, sort of. This 1 over t squared is actually not technically a polynomial. And we stated previously that undetermined coefficients can only be applied when the g of t is either the sum or product of polynomials, exponentials, or the primary trig functions. So that indicates that I cannot apply our previous method to this specific differential equation. So anyways, I just wanted to point that out. Let's go ahead and get started applying the variation of parameters method. As usual, our first step is to solve the homogeneous version of the differential equation. I have a single repeated root. So we know from earlier in the chapter that the two functions that I'll use to build my general solution are these two here. And whereas in the previous method, I would actually write out that general solution, here I'm going to go ahead and keep those ingredients isolated. I'm ready to set up and solve the system of equations that we just derived a second ago that sort of serve as the core of this method. Here's a reminder of what that system is in general. I have my y1 and my y2, just stated those. y1 prime and y2 prime will be easy enough to calculate. And then as a reminder, the u1 prime and u2 prime are acting as the variables in this system. So they're what I'm going to actually solve for. Here I've plugged in the specific y1 and y2 that we just stated, along with their derivatives, into this system. Now the algebra here can be a little tedious, but hopefully it works out to be okay. In this particular system, I feel like I want to multiply this top equation by 2, and then these u1 prime terms will cancel if I add the two equations. Here I've multiplied that top equation by 2. Now let me take these two equations and add. That gives me this equation here. Now I've got some cleaning up to do in this equation. I guess right off the bat I would note that every term, even once I've distributed through these parentheses, every term has an e to the negative 2t in it. So just to kind of clean up the algebra a little bit, I'm going to divide the entire equation by e to the negative 2t. That yields this equation here. Now if I distribute through the parentheses, I guess here I'll have negative 2t u sub 2 prime, while here I have 2t u sub 2 prime. So those are like terms, so those will cancel, and then I'll just have on the left hand side u sub 2 prime equals t to the negative 2. So on the one hand, that's kind of my answer. I guess on the one hand, I'm going to want to anti-differentiate this. So I'm going to want to integrate this. That gives me this expression here. On the other hand, I'm going to take this and plug this back into one of my original equations in order to be able to solve for u1 prime. Before I do that, let me just point out in this u sub 2, since I anti-differentiated, I need to introduce a constant of integration, and I've called it c sub 2. This is one of the solution functions that I'm trying to work to solve. So let me put a box around this, and then my general solution will be built using this u sub t. Before I do that though, let me take this u sub 2 prime, and let me go ahead and put it in this first equation, and then that'll allow me to solve for u1 prime. Here I've made that substitution into the first equation. Let me simplify. Again, it looks like I can again divide by e to the negative 2t. These t to a power terms will simplify. I should be able to get u sub 1 prime pretty directly. Believe I get u sub 1 prime equals negative 1 over t. Anti-differentiating that yields this function for u sub 1, negative natural log of t plus c1. So I took the stated system of equations, which was in terms of u1 prime and u2 prime. I did some algebra. The algebra wasn't too bad in this case. That enabled me to identify u2 prime and u1 prime, and then I anti-differentiated each of those to be able to identify u2 and u1. My last step is to build my general solution. So here is my general solution. I took u1 times y1 plus u2 times y2. That's it. I'm done with the problem. There's actually a couple things I do want to point out though. First, just real briefly, notice that if you were to distribute through the parentheses in this general solution and then rework your terms, rewrite your terms a little bit, you would get something that looks like this. And notice that in this reworked form, my y sub h, the solution to the homogeneous version, does show up here as just c sub 1 e to the negative 2t plus c sub 2t e to the negative 2t. And then to that y sub h, I've added some new function. So based on the theory from the last couple sections, we know that this function is acting like our y sub p. So my general solution does have the structure that we pointed out a couple sections ago, where I'll have y sub h plus y sub p. On the next page of notes, I want to highlight a slightly different approach to enacting the method of variation parameters. As we just saw in that example, this method basically boils down to solving a system of equations. I can be even more specific. I know that since we're dealing with second order differential equations, our system will always be a 2x2 system. We saw in section 3.6 that Kramer's rule gives us a direct formula for solving any 2x2 system. This is a restatement of Kramer's rule. If my original system has this structure here where x and y are the two variables I'm solving for, then I can directly identify the solutions for x and y using these two determinants combined in an appropriate way. So why not try to apply Kramer's rule to the system that we need to solve when doing variation parameters? Here's a reminder of what our system looks like. I'll remind you too that the variables are u1 prime and u2 prime. So the coefficients are y1, y2, y1 prime, y2 prime. And applying the structure of Kramer's rule gives us these direct expressions for the unknowns u1 prime and u2 prime. What's even better is that each of these numerator determinants includes a 0. So when I calculate this determinant for u1 prime, for example, I'll do 0 times y2 prime, so that'll just be 0, and then I'll have minus y2 times g of t. Similarly, in this numerator, since there's a 0 present, my actual determinant will just be the product y1 times g. And then hopefully you recognize this denominator. You may or may not, but this denominator is the wronskian of y1 and y2. So I can simplify each of these determinant fractions and write them in a more concise way as I have here. So these two formulas directly identify the u1 prime and u2 prime that we were solving for in the system as we did in the previous example. And if I look at these formulas, most of these ingredients are pretty readily available. G of t is stated directly in the initial problem. y1 and y2 I get pretty quickly by identifying the solution to the homogeneous version of the differential equation. And that leaves just this wronskian to calculate. It could be a little tedious, but it's just y1, y2, their derivatives, and then I just have to calculate the appropriate determinant. So utilizing this structure could potentially be pretty convenient. We'll demonstrate this approach in example 2. In example 2, we're going to consider this non-homogeneous ODE. At first, I haven't specified a right-hand side function g of t. That's okay, because my initial step always centers around what's happening on the left side of the differential equation. Here I've identified the solutions to the homogeneous version of this differential equation. I've called y1 and y2 these two solutions that form a fundamental set of solutions. And then I'll go ahead and calculate the wronskian of these two solutions because I know that will be required in the solution method that I'm using now. And it looks like that wronskian equals e to the 5t. So I've laid out most of the ingredients that are required to enact this Kramer's rule based approach to variation of parameters. Now in part A, we're finally given a specific g of t, a specific non-homogeneous term. And so I have all the ingredients necessary to move forward with this approach. Here are the general formulas as a reminder. I've plugged in all of the necessary ingredients. All I need to do is simplify. So now I have my expressions for u1 prime and u2 prime. Next, I'll anti-differentiate those to identify u1 and u2. As usual, I'm running out of room, so I'm going to try to squeeze this into this last little bit of available space. I get these two functions here for u1 and u2. And I put all my ingredients together to come up with my final solution given here in this light green box. I am going to scroll to the next page just a little bit to give myself a little room because there's a point that I want to make about this general solution. Notice that if I distribute through these parentheses, these exponentials will simplify, and so the actual appearance of my general solution may look a little different. Let me go ahead and do that, distribute through these parentheses, and then regroup my terms in a slightly different way. So here is an alternative form of that same general solution where, again, all I've done is distributed through the parentheses, collected like terms, rearranged my terms in a slightly different way. There's a couple points I want to highlight here. First, I notice again that the y sub h, the solution to the homogeneous version of my differential equation, is present, and that means that this must be my y sub p. If I look back to this original g of t, this is a sum of exponentials. So this is the type of problem that we could apply undetermined coefficients to. And if I were to use that approach, I'd have to be careful to note what we called repetition between one of the terms in my y sub h and one of the terms in the y sub p. And then if you recall from the last section, we have to modify our y sub p, we have to make adjustments to it, etc. Using this approach, that detail never came to light. We just moved forward with the approach in the standard way. We didn't have to modify it at all. But notice that this method does make accommodation for that repetition sort of on its own. If you look at my y sub p, first of all, I have an e to the t term, which I would expect because there's an e to the t term in my g of t. So those terms match. This term here came from the fact that this e to the t was present in my g of t. And then when I look at this second term, the e to the 2t, we know that because of the repetition between that term and the similar term that we identified in our y sub h, we would need to multiply that by a t. And that t, e to the 2t term, the coefficient of 1 in this case, does show up in this method. So I just wanted to point out that those considerations of like repetition that we discussed in the last section are all accounted for in this method. I can just apply this method directly and it takes care of all those details for me. Let's go ahead and take a look at example B. In example B, I'm going to reuse the same differential equation. This time I'm going to change the right-hand side to be this given g of t. Notice that this g of t involves a t to a power term that is not a polynomial. So unlike part A, we could not apply undetermined coefficients to this differential equation if we wanted to. I'll be reusing most of the same ingredients that I used from part A, the same y1, the same y2, the same wronskian. So I think I'm ready to just plug some expressions into the formulas given for u1 prime and u2 prime. Plugging in the appropriate ingredients. These are the two expressions I get for u1 prime and u2 prime. And I just want to point out that as I wrote this out, I realized that I forgot this negative on part A. So in the notes, I went back and I fixed it. But if you watch the explanation I just did, I'm missing this negative. This negative is required in the formula. So check the notes to see how I made that correction. Now I will simplify these expressions and then I'll try to anti-differentiate. So I get these expressions for u1 prime and u2 prime. Let me go ahead and anti-differentiate. u1, straightforward enough, but for u2, I actually have an integral that I can't evaluate analytically. We mentioned at the beginning of the notes that since this method involves integrals, there's going to be occasions when I run into integrals that I don't know how to evaluate. And this is exactly one of those occasions. So on the one hand, it feels like I can't write out my full solution. But on the other hand, if I'm okay having an integral as part of my solution, then I can still build my general solution using this integral that I don't know how to evaluate. Just to be a little bit more precise, I should actually rewrite this integral as this definite integral, where I integrate from some fixed starting t value up to the variable value t, and here in my integrand I'm forced to change the variable. It's the same integral, but since t is actually acting as the independent variable here in this function, the variable within my integrand has to be something else. I've picked m, but I could have picked any variable. So let me go ahead and write out my general solution, and I will include this expression for this integral that I can't directly evaluate. So that will be my final solution. I admit it's a little dissatisfying to have our final answer in terms of an integral, but there are in fact a lot of instances where the functions that we're dealing with are just too complicated to be able to identify all of the integrals analytically. If I found myself in that sort of situation, I could easily use a computer program to numerically approximate this integral, and then that would allow me to get numerical approximations of my general solution, even though I can't analytically identify the antiderivative of this function here. And actually, while this seems like a sort of drawback that we've ended up with an expression that involves an integral we don't know how to evaluate, in a certain sense, this is the real strength of this method, variation of parameters. To demonstrate that, let's take a look at part C. In part C, I now want to solve the differential equation for an arbitrary g of t. I'm not going to specify a specific function for g of t. Let's see what that looks like. So here I've simplified my u prime expressions as much as I could. Again, I don't know what g of t is, so I can't simplify them any further than I've got written here. So then when I go to anti-differentiate, if I don't have a specific g of t, I clearly can't specifically evaluate that integral. So instead, I would write my u sub 1 and my u sub 2 as I have here in terms of these general integrals. Again, this may seem like a big drawback because I don't have a specific solution. It's just going to be in terms of these unknown integrals. But in many contexts, I may want to evaluate the differential equation for a wide range of g of t functions. And this approach allows me to write my general solution and then potentially evaluate this general solution, maybe analytically or maybe just numerically, for a wide range of g of m functions. So even though for certain functions I won't be able to get an integral that I can actually evaluate, one of the strengths of this approach is that it allows me to write this general form of the general solution before even having to specify what the g of m function is, or the g of t function in the original differential equation. So that concludes section 3.9. In this section we've discussed variation of parameters, which gives us an alternative method for solving non-homogeneous differential equations.